So actually, he's not the last speaker. Next to last speaker in the series today is Professor Fulvio Domini, who works at Brown University, and he spends a lot of time at Princeton, and he frequents very much at Rutgers. We have the pleasure of working with him quite often. So he is concentrating on whether structure from motion can reveal the true Euclidean real structure of the world. And he has some challenging notions to the issue of whether we can indeed get the vertical layout, spatial layout of the world, which he will explain today. The title of his talk is the goal of three-dimensional vision to recover the Euclidean structure of the world? Question mark.
Thank you. Well, obviously I'm honored to be here for this event, and which is very important to me actually, because just a few years ago I was this grad student in the psychology department in Trieste, Italy, which is the galaxy far away. And I started grad school, and as many grad students, I had no idea what to do, right? And so I was totally lost. And at one point, this guy, who is now a professor in Florence, Corrado Caudec, came to me and said, here's a paper that you could read and see if you can model this stuff. Because I have another paper I want to submit, and I want to model the stuff and include it with this paper, okay? So he gives me this paper, and I have to say, this is not, I know it sounds cheesy, but this is what really started my entire career. For good or for bad, I would be here if I didn't read this paper. And this is the paper, okay? So now, this is actually the real thing, and I found it and I saved it because it's so important to me. So I have this in my presentation at Brown University, where they hired me as a result of the work I did on this. And you can see this is, in Italian times, so all the notes I took and I wrote were in Italian, and so I'm not embarrassed to show it to you because otherwise I wouldn't show you. Right? So, and the paper is called Affine Structure from Motion, which actually Jan a few years ago told me that was absolutely uncited by psychologists until a computer scientist discovered it all of a sudden, and and made it out to be this very great paper. And so, you see, I understood some stuff about the slant of the tilt and so forth. So, after reading this paper, where Jan Koenderink is providing a new way of thinking about 3D structure, instead of looking at 3D structure as a physicist would do, where you think about taking, or at least a Newtonian physicist, where you think about objects in terms of Euclidean geometry, and you would think that maybe the visual system works that way, recovers the Euclidean geometry of 3D shape. Jan said, well, if you take only two images from a structure from motion sequence, so if you just take the velocities of a sequence, then you cannot derive that Euclidean geometry, but you can derive what is called the affine geometry. And so this observer here is looking at that image there, and a way of thinking about what the affine structure of that shape would be, seen from above, is a class of objects. Instead of being one object, is actually an infinite family of objects, which are stretched in depth through a linear function. That's why they maintain this triangular shape. And so, just to give you an idea a little bit more in terms of mathematics, and since I will be using this throughout my talk, just keep a couple of facts in mind here. Okay, so here you have a shape, which is this triangle, and imagine an observer moving the eye from left to right here. This produces a kind of an angular rotation around the object. Okay, this angular rotation done in time, okay, which is called omega here, produces a change in the projection here between the vertex and this part here. Alpha 1 and alpha 2 are the two angles you register with your eyes, right? And the difference between these two angles, vulgarly speaking, is the velocity, the image velocity, okay? So that's the information you get. This is a very extremely rarefied and simplified version of what this is all about. After you get that, then you can see that that velocity, which is the visual input, is related to z through this ratio here between omega, the angular rotation, and the distance to the object. Just to tell you that there is a constant here, kV, okay, you will see throughout the talk. And this constant represents what you should need to have to derive the actual Euclidean structure of the object, okay? So once you get that constant, when somehow you know how much you rotated your head, or you get what is called second order information from the optic flow and so forth, it doesn't matter. Once you get that, you are able to get the Euclidean structure, okay? So my interest at that point, after reading this and after knowing that the affine structure is actually all possible shapes for all possible kinds of constants, I thought, okay, what is going on with structural motion? This is how I started studying structural motion. And just to correct you a little bit, I used to do structural motion, I don't do it anymore. But we came up with kind of a theory, what structural motion is all about, by trying to understand what is this constant that the visual system is deriving from a 3D image. And what in a very watered down term we found is that the structure you get has nothing to do with the structure you simulate on your computer when you produce a structure from motion stimulus. In other terms, you find that from motion is simply a monotonic function of what they call the velocity gradient, or the V that you saw before, okay? And in general, you never get this correct constant that would give you the Euclidean structure. Okay, so this is the basic of all this work I've done on structure for motion. Of course, we didn't limit to this, but the point is that if you plan your experiment right, then you see that you will, subjects are not able to get this actual information. Okay, so if you keep this in mind now, let's move on and see what the field was at that point. So I was finding this, and other people in our field were finding this, but still out there, and I think they're still around, are those who think that the goal of the visual system is to get the Euclidean structure of the world. So, like the physicists would like to do it. Okay? So you have signals, and in this talk I'll restrict my conversation. Hopefully I don't get any Skype calls. My conversation to retina signals. One is the velocity, and one is the disparity signal. Okay, and these two are very similar to each other. Okay, the velocity, as I said, could be given by the rotation of the object, or the rotation of the head, or the translation of the head. The other one is given by the two eyes that are slightly displaced in space, so they take two pictures instantaneously. Okay. The bottom line is that both these two signals, to get you the z, so the depth of the object, so from now on, depth is the only thing that you have to think about, you need to recover what I call this kV and kT, which I call inverse geometry parameters. So these parameters allow you to take the disparity information, the velocity information, and then transform it back into the structure that has projected those signals. Okay? And the idea of Euclidean scaling is that you have these inverse geometry parameters that are estimated somehow, the signals, and you get a 3D model, which is very difficult. And this gives rise to perception and action. And I will talk about action and perception later again. But to go more in a little bit more in details how it's done, and this is another important point here for this talk, is that once you get these signals, then you have dedicated modules that analyze these signals, and each module provides an estimate of the property, the Euclidean property in this case is depth. And this estimate obviously is going to be something that is noisy, right, with a certain variance in the representation, the 3D representation. So if you get an estimate of 5 centimeters, then you can have 5 centimeters plus minus 5 millimeters or something like that. And each module has their noisy representation. Then there's a way to combine this representation to a weighted average, for example, but there are more complex ways. And this weighted average is going to give you a new estimate which is more precise than the one provided by each module separately. Okay, so it's a new estimate, and you can calculate the variance of the new estimate, and that's going to be better. So it's going to be a smaller variance. Okay, so this is the idea underlying this Euclidean representation. Okay, and I call it the Euclidean representation assumption because I don't think that we have actually empirical evidence that that's true for the visual system. Actually, I think there's a lot of experimental evidence which speaks exactly to the contrary of that. Okay? So now, the question is, how, and this is really my question today for you also, right? I've been thinking all these years, I'm sure that Jan has multiple answers to that, is how would the visual system evolve to discover the Euclidean structure of the world? And how is the ground truth discovered, right? You need some sort of a ruler. What is this ruler that we got? And many times I get this answer as if like, well, it's through evolution, but that's a little bit of, a dismissive answer to this question, right? What ruler serves the purpose? And so I think that, my way of thinking about the problem of the division is like, let's go back and think what the division is for. The division is really for interacting with the world, right? And our perception of the world is something that comes after that, but the most important thing is interacting with the world. And so you have to seek this information that allows the appropriate mapping between the visual input and the motor action. You have to organize this information, this useful experience, which is perception, okay? And then, another thing I want to add is that to learn this mapping, remember, you don't have a rigid ruler, but you have stuff that moves all the time. If you think about humans, if you think of some animals, they are squishy and so forth. Okay? So you don't get this rigid ruler that Euclid came up with. And the mapping actually does not necessarily need this veridical meta information. This is what I think instead is going on. So here's the conjecture for you today, and then I will connect this conjecture with another sub-conjecture that brings to a model that I developed actually a few years ago that now I revamped because I liked it more this way than the way it used to be before. So, but since you don't know this model, it's all new for you guys. So it's like watching a movie. So the conjecture is like how learning to see in 3D may happen, right? And what I'm thinking is that the only space where you can really learn about the structure of objects, right, where you can actually run experiments yourself is the personal space, okay? So here you have an example, anybody who had kids or have kids have observed these things. So this personal space is where we can explore the 3D shape and where you can actually start organizing information to provide this useful motor mapping. So if you have an object, for example, where the property of importance is Z, to simplify, so grasping it along the dark dimension, this object produces some signals. In this case, I reduce it to just 2 signals, right? Forget about interreflections here. There's only disparities and velocities. And these 2 signals are going to somehow create a motor command. Maybe at the beginning you're very clumsy, then you get there, okay? And then this motor command is constantly calibrated. So I can see this going on all the time, right? You grasp, you calibrate, you grasp, you calibrate. It's a continuous calibration. I think this calibration is going on up to adulthood or until you die. And the way I think about perception, and here we're a little bit philosophical in a way, is the awareness of this moral command, of this initiation of this plan, of this possibility that visual input gives you. Okay. So now I get to the other part of the follow-up of this conjecture is that, well, if you think about the personal space where you interact with objects, this personal space is very limited. Your arm cannot stretch like those guys in the sci-fi movies. You can only move of a certain amount your head. All this stuff is limited. Okay? So really, and this is the silliest MATLAB simulation that anybody can do. I said, okay, I just simulate an object of a varying depth, okay, with a certain possibility of positions, which I think has a 40 centimeters variability, and certain possibilities of movement of the head. And when you measure the velocity and the disparities in terms of radians here, what you get is that there's a very, these signals are between them, okay, and of course they correlate very well with the depth of the object. So in a very stupid way, if you think about this as being, I'm not proposing that this is what's going on in the brain or this is the learning mechanism, I'm just thinking with you about it, is that the situation in which you learn stuff is very limited, okay? And so in this case, the signals are not that ambiguous in a certain way, but you do not have the possibility of exploring the rest of this space. So again, here's the velocity, here's the disparity, and here is all the possible velocity and disparities, and the information is along this dimension here. This is where depth is, okay? And so if you learn only this space, you may not be able to understand what's going on outside of this space, okay? It's a very silly system, okay? So, and the simplest way of doing this, the computationally trivial way of doing it, is what is called principal component analysis. You take away the noise, which is orthogonal to this dimension, and you take all the information along this dimension. And for what this talk is concerned, just consider that this thing, which I have called from the beginning rho, and I'm going to keep calling it rho. Rho is the magnitude, okay, of a vector. We'll see it in the next slide. But anyway, so this scores around here is where the information is. And my claim is, and for this I will provide empirical data, is that the motor mapping and perception are function of this thing, of rho, which is not necessarily the thing that gives you the Euclidean structure. And again, this mapping, this what I call psi here, doesn't need to be a linear mapping. It just has to be some mapping that allows you to grasp the object. Okay? All right. So now, this is again the space here, if you look at this training set, basically doing a PCA is finding the length of this vector. Okay, so now the idea is that what happens when you have something that is outside of that training set? What does your visual system do? And my claim is that your visual system simply takes the length of any vector within the space because it has learned a function. And this function is simply the sum of the square of the disparity of velocity scaled by something that I'm not going to go through it now, but it's not important. Okay? So once this function is learned, it generalizes for any combination of image signals. And so the idea here is that if you have a pair D1 and V1 within the learning set, a pair DV outside of the learning set will produce the same value of depth if rho, or the magnitude of those vectors, is the same for the two. Okay? That's the hypothesis. Now, the second thing is the discrimination according to this model. So, by the way, I call this, did I correct it? Oh, yeah, okay. I call this intrinsic constraint model assumption, which is something that is, has now a name as few years, at least for me. So Now, what does it mean to discriminate according to this model? So when I told you about the Euclidean models before, remember I told you that you have multiple modules, and each module provides a noisy estimate of depth. And then these noisy estimates are brought together, and that's what produces a better accurate measurement of depth information. Now, for me, these estimates are not noisy at all. The only thing you have to deal with is discriminating two stimuli, but this has to do how the stimuli are being encoded once you experience them in the world. And let me explain to you what I mean by this. So, I said that rho is what determines a function, okay? And so that the perceived depth is a function of this quantity rho, okay? And this function may be nonlinear, probably not even like this, is some in another way, it doesn't matter, okay? And now, the idea here is that you do a sampling in this learning process that has to do with something like, for example, the statistical of objects that you're grasping, or something like this, right? But my point is that the discrimination, so the granularity of this space, and I'm talking about now the perceived space, or the motor space, okay? The granularity is fixed. Once you have a certain value of depth, you know that depth can be discriminated from an object that has a depth of plus 2 millimeters, always, okay? And so that means that it's nothing to do with the signals, all right? So you can have multiple signals, one of these signals give you a perceived depth of z hat here, then they have to change by an amount that produces a change of z hat plus delta z hat, where delta z hat is what represents this granularity. And this change is what I indicated by rho plus delta rho. So this vector is to change by this particular amount, okay? And that amount is given obviously by this function. It doesn't matter, you have to take a derivative, which is basically the slope of the function over here, right? But my point is that you can, no matter what is produced, no matter what is producing rho, this vector, if it's only velocity, only disparity, all together, texture, whatever you want, the important thing is that you, the change in that vector length that allows you to discriminate two stimuli is going to be always the same. And this is a very important, very important prediction. So, in brief, we have two predictions for this model. One is that two combination signals elicit the same depth estimate when they produce the same vector length rho and rho1 here. And when two signals elicit the same depth estimate, then they will need an equal change in their length in vector magnitude to be discriminable. Okay, so these are the two hypotheses. I'll provide some data that maybe convinces you that it could be right, or maybe there's another model that explains it, but this is the idea. So now, in many experiments that you have read or you haven't, but that present the problem of Q integration, you see that people do these things called, I do a single Q experiment and then I do combined Q experiments. Or there are people that all their career, like at the beginning of my career, did only structure from motion, right? And these are what people call single Q stimulus. I'm just testing the module that has to do with structure from motion. Or I'm just testing the module that has to do with stereo. My idea is that there's no such thing. You are always processing everything because that's how you learn stuff. They work all together, okay? And when you do single Q experiments, you're just turning down one of the stimuli in a certain sense. You're just putting it to zero. It's like, taking part of the brain that processes disparities out. Okay, so that's in simple terms what I think you do. So if rho is something like the disparity signal squared divided by this factor that has to do with how you learn this function is unimportant now. basically when you do a disparity-only experiment, then you are reducing everything to a vector along the disparity line here. And if you do a velocity-only experiment, then you are producing a vector that goes only along the velocity dimension. So here you have zero velocities when you are up this axis. You have zero disparity when you're along this axis, and the combined Q stimulus is this one. Okay? So for simple math, really, I mean, it is then this kind of rho thing here is going to be these two components, right? So the rho d, which is the disparity vector, is going to be this thing here. Okay, so kd divided by d times zd, which is the depth from disparity, or you're going to have a rho v, which is only kd divided by v times zv, which is only the velocity depth. Okay. So now. Okay, so yeah, this is what I told you. Sorry. All right, so then, this is the important part because I'm going to make the prediction here. So, when do single Q stimuli appear matched? All right, so that's the next question. And now, from what silly rule I told you before, so this learning mechanism that basically associates any vector with the same depth once the vector has the same magnitude, you're going to have that the depth from disparity is equal to the depth from velocity when rho d equal rho v, or when these terms are equal. And you are going to have that since these vectors are the same length, then the discrimination, the amount of change of these vectors that is needed to provide a discrimination threshold, when you can discriminate to stimulate 75 or 85% of the times, is given by this equation. It's very banal. You just take this equation and you put delta instead of just ZB and ZB. And if you put these two equations together, you're going to get this thing here. Okay? So this is a very weird statement. So two stimuli are matched, no matter what that depth is, when the ratio between the just noticeable differences that I call delta here, don't call J and D, I don't like the name. Delta ZBD and delta ZB, where the ratio between the just noticeable difference and the actual intensity of a stimulus, when these two ratios are the same, then they're going to be perceptually matched. So we did this a few years ago, and we first had a fixed motion stimulus, which you can see over here, and then let's see. It's less exciting than your stuff. Oh. And it's also crashed the computer. Oh no. Okay, good. Let me see it. Okay. Oh, all right. So very simple, right? So you have a random dot stereogram. If you can cross-fuse, but they're too far away, sorry about that. And then, you know, a bunch of dots, and then you have those three rods, and you have to judge the depth of the three rods, right? So the experiment was, I show you a structure for motion stimulus, it goes away, then I show you a stereo stimulus, and then you have to adjust, or through a Starkist procedure, or psychometric procedure, the stereo stimulus until it is perceived as having the same depth as the motion stimulus. So let's go back to the presentation. Okay, so now you do that and you find a PSC. Okay, so this is the point of subjective equality that determines when the disparity stimulus is perceived as having the same depth as the stereo stimulus. Okay, and this is the results. So these are different subjects. These are two different depths for the motion stimulus on the x-axis. On the y-axis, you have the results. So you see high between subject variability. They're inaccurate. Here there were actually two distances simulated, and so forth. So it's all over the place. Okay? So now, we wanted to test our theory. We said that two stimuli are matched when the ratio between the J and D and the depth is the same. So we measured the J and D. And these were complete separate measurements. We took the velocity stimuli, we estimated the J and D through the slope of the psychometric function. We took the disparity stimuli, and we found the J and D for those. And so we go from here. This is, say, the Euclidean hypothesis, how Euclidean guy will tell you is what you predict, which is you have to be on this line here. Okay, this is the veridicality line. And this is our hypothesis, that is the ratio between the discrimination threshold and the stimulus, J and D, just in a more familiar jargon. And then you get the prediction is that the PST of disparity should be the depth of the velocity stimulus multiplied by the J and D of the disparity stimulus divided by J and D of the velocity stimulus, which is completely weird. But these are the results. I remember that when I submitted this paper years ago, I got rejected because they told me that one point was a little bit too out of the thing, and I wasn't really predicting the results, right? So anyway, so then we insisted, and when we went on, we went down to another paper we published before. We said, well, wait a minute, let's see with that paper if that's the case, right? And so here's the results. And you don't look at the blue things because they look the same here, right? These are the unscaled results by the J and Ds. Here you have the PSC of the velocity stimulus, PSC of the disparity stimulus, and this line that is off range here would be the veridicality line. Instead, you are here, okay? Completely off, right? So a stimulus of 30 millimeters is perceived as 12 millimeters for disparity. It's like more than half. But then if you do this thing again, here you have this perfect match from the predictions. They are based on this and the measured PSD of the disparity. So, now let's go back to the idea of Euclidean representation. So, there is obviously this dissonance with this idea because we saw that this thing cannot be described as veridical extraction of 3D shape from motion or from stereo, right? But, and you see these huge biases. So when you read these papers though on Q integration, you realize one thing, and correct me if I'm wrong, you realize that are concerned about the precision of the measurement. They say, if I take Q1 and Q2 and put them together, I have a better measurement. And they prove it by showing how the results are well matched with this equation, that where the variance of the combined stimulus is going to be smaller through this simple equation here, okay? So this is the stuff as being supporting kind of the camp that I'm criticizing. Now, what happens with this model here for multiple Q stimuli? As you've seen, verticality is not an issue here, right? So now, if you have multiple stimuli, now you have that after you do your single Q experiment, which is this vector and this vector, the multiple Q stimuli vector is going to be longer. So what I told you before is that the length of this vector determines your perception. I don't know what the function is, but it's a monotonic function. Okay? And so what happens is that combined Q stimuli should always appear deeper than single Q stimuli. Always. Okay? And so this is the first prediction. And the second prediction, and I apologize for all these equations. So Jan, if you don't understand them, I'll tell you later how to do it. And so, but the idea here is that if you take this function, I really like this, so I would like to go through it. But so take this vector, right? This vector is this representation, right? This square root of these terms multiplied by z. So if you take this vector, you take a derivative, or you do like a little variation, delta rho of this vector here, the just noticeable difference that you measure, then the delta rho is going to be this term times delta rho, delta d, delta z of this, delta z of the combined stimulus. And the same thing for the single Q stimuli, okay? So you have 3 delta rhos. Now, if you're in a region of the function where these vectors are not that much different from each other, where you don't have these gigantic Q conflicts, then you can consider that this variation here, because of the theorem I just told you before, the prediction of the model, is that delta rho, they produce this, since these vectors are similar in length, then the variation is going to be the same for all of them. And if you combine these equations, you get this prediction here. So the prediction is that the threshold of the combined stimulus squared is going to be equal to the threshold of each stimulus squared times the other stimulus squared divided by the sum, which is exactly what the Euclidean model predicts. So this part of the equation is perfectly predicted, okay? Now, you don't need to assume any representational noise with this thing. It's all about, I have stimulus 1 and stimulus 2. I've learned a certain granularity, so I can just discriminate depth of 20 from a depth of 22. It doesn't matter what stimuli I use to produce this depth, and you get this result out. I can guarantee you that. Now, a while time ago, with Max Di Luca, who is now between Oculus and Birmingham, and he was my graduate student, so this is his thesis. He did this experiment where you had multiple cues, velocity, shading, and texture, and an object like this, which is a paraboloid. And he had a bunch of judgments made on this shape, which could be the curvature at the tip, the slant at a certain position, and the depth. Okay? So now, these are the results. So let me like explain to you what actually I didn't go through the methodology. So the subjects, what they did, they were seeing these pairs of stimuli, and they were matching a 3Q stimulus where you have all these things, velocity, shading, and texture, with either a single Q or a 2Q standard stimulus. So a stimulus which had a fixed depth of either 3 centimeters and 5 centimeters. And the match was done with respect to all these properties. And then I'll tell you in 1 second why we did that. And let's just check the depth, the results for depth. Okay, so on the left side here, you have the standard stimuli. Remember, the standard stimuli simulate the depth of 3 or 5, okay? The white things are those with 3, the responses of stimuli that had 3, and the gray is the one that had 5, okay? And remember, this S, where you see S is shading, T is texture, V is velocity, and ST is 2Q stimuli. Shading texture, velocity shading, and velocity texture. As you can see here, the results are all over the place. First of all, just look at the white things, okay? For the 3 centimeter stimuli, you see that what you get from shading is different from what you get from texture, is very different from what you get from velocity. And also, the 2Q stimuli are even longer, so they are perceived as being deeper. Okay, so 1Q is less deep than 2Qs, and of course, we have a 3Q stimulus, and we don't know anything about the ground truth of these judgments. But what is interesting, and I won't go to it, is that if you take those equations with the vectors, which are very simple to manipulate, then you can actually predict from the PSCs you get here, of shading, texture, velocity, what the PSCs of the 2Q stimuli will be, okay? And so this is what we plot here, the predicted PSC and the observed PSC. And you see that we're pretty much in shape. So, non-veridical, all over the place, you apply this simple rule, you get a very good correlation. No correlation, sorry. I'm not talking about correlation, I'm talking about prediction, because this line here, and I forgot to tell you also the other one, there is no free parameters here. I forgot to tell you, it's very important. No free parameters, and this 45 degrees line is a no free parameter prediction of the model. And the same thing you get for other judgments, slant and curvature. And if you kind of have a little bit of a memory thing, you see that all these bars are different for curvature, slant, and depth. Because this is another thing we discovered, is that when you talk about local properties, you don't have a unique representation in your head. You have different things depending on what are the metric properties you're asking the subjects to judge, right? And anyway, for example, shaping stimulus is going to be good in telling you how curvature changes in a shape like this, right? But it's going to be really bad in telling you how much depth varies. If you try it yourself, by simulating something, you see the depth doesn't vary that much, but the tip is going to increase until it looks like a cone. All right, so, am I good with time?
Yep.
I'm like,
Yep. 10 more minutes.
oh, 10, okay.
Yes.
Well, so long, extremely good time. So then we said, okay, let's move on and see if it's true that also grasping is influenced by this kind of biases. So because our claim is that perception and action are just the two sides of the same coin. And in fact, we are kind of against this. We are suspicious about this theory that says that there are two visual streams, and one visual stream apparently has the ground truth because you have to grasp. So that's the action system, which apparently, allegedly, is done by the dorsal stream. So we think there is only one processing, that this processing produces a motor action, but also produces your perception. And so we do this in our lab where we have kind of a complex system with monitors that can move back and forth, and the subject's movements are tracked through what is called the optotrack system, where there are infrared sensors that emit signals that are registered with very high precision. And this is kind of the lab. And this work I'm presenting is the thesis of Carlo Campagnoli, who is now actually postdoc in Princeton by chance. So Carlo did this experiment where people had to judge shapes like this, cylindrical shapes, and they basically were seeing what kind of aspect ratio they were getting. So the aspect ratio would be the ratio between the depth of the stimulus, delta z, and delta x is the size of the stimulus. And so this is in the physical space. You can see this. We tested this at two different distances, a close distance and a far distance. And what we observed in the past, and I presented in the last talk I gave here a couple of months ago, is that the physical shape space and the shape from stereo space are not similar, but you have what I call a lack of shapes constancy in the sense that objects that are close to you appear more elongated, and objects that are farther away from you appear shallow. Okay, so this is a lack of that constancy. If you were veridical, it would be along this line. Now, we thought, okay, let's do a multiple Q experiment. So if you're bad with that, and that you have this lack of shape constancy, which is revealed both in an action task and in perceptual task, then you should be maybe better if you provide more Qs. And so we added other Qs, and we added a motion Q and a texture Q. And without going into the details, I can tell you that these kind of Qs are such that they are invariant with distance. So if you take an object, you expand it, the texture gradient is going to be the same. So the shape is going to stay the same. Okay? So we combine these two things together. We said, okay, now we put some shape from motion and texture, and these things should give you constancy, which is the horizontal line you see over there. Okay? So if that's the case, then we should get some combined estimate according to the classical Q combination models that is somewhere there in between. And so he did this experiment. He had various depths, simulated depths, two different distances, two conditions, stereo motion, and we had some devices to not allow the view of contours. And people were making two kinds of judgments. One was a perceptual judgment. In this case, was done with this manual size estimation. So place your fingers such that the distance between the fingers that you perceive is the same as the perceived depth of the object. And these are the results. So for the close distance, you can see here that the stereo motion stimulus, this is what is important for the presentation today, actually. The stereo motion stimulus is perceived as, this is the close distance, perceived as being more elongated than the stereo-only stimulus. So the two Q stimuli, the vector that I showed you before is larger, and in fact the two stimuli are perceived one deeper in the other. And we didn't get better with depth constancy. You can see that anyway, when you added motion, this depth under constant, the fact that the close stimulus perceived as being deeper than the far away stimulus stays there. So you get worse, or the same, but you have this thing that multiple skew stimulus are perceived as being more elevated, as predicted by the model. Then we did this with grasping, and here you see these snapshots at the time of the maximum grip aperture, when you go and you envelope the object, and when you're approaching the object. And what you get is that when you observe what happens with, it's the wrong button. When you observe what happens with the grip aperture, forget about the MGA for now, is that you have lack of depth constancy because the object's closer and grasp with a smaller grip, larger grip aperture, the object farther away. As in perception, you have exactly the same pattern. Here you have grip apertures at different distances from the object, and also the stereo motion stimulus is grasped with a larger grip aperture than the stereo-only stimulus. And this is the only thing you have to remember for now, okay? And now, we did the same thing with texture, and we got exactly the same results. So these are the perceptual results. If you have texture, nothing changes. You have lack of depth constancy. Here's the object distance. Here's the manual size estimate. And also, stereo texture stimuli appear as deeper than stereo-only stimuli, okay? Same thing with the grip aperture. So what's going on here? Well, somebody who may criticize these results would say, well, what about Q2 flatness? There are things on the monitor that makes you think that the monitor is flat. So you have to test these things in the real world to tell me that they make sense. So we did that. And this is the third part of Carlos' thesis, and it's all stuff that we have just submitted to publication. One is under review. And so now our observer was seeing a real object. The real object looked a little bit like this. It was a prism. And the way we manipulated the information is by adding stereo. So we painted on an object, then I showed the actual object, these stripes, these horizontal stripes. They were white, illuminated with a wood light, one of those ultraviolet lights that makes it appear light. And so when the object is horizontal, there's no stereo information because these lines are all horizontal, so the two images are exactly the same, the two eyes. And so if you rotate it a little bit, then you get stereo information. And the important thing here is that we didn't want stereo to become overwhelming over the other cues we used. Okay, so that's the reason why we did this manipulation. And then we added also motion information by rotating this thing, so you can actually put the object and have these lines in a certain direction. Then you rotate the object, and you get motion information and stereo information together. And obviously, this was in a room, in the messy room we have, chin rest and so forth. The subject was grasping a real object, and the real object was something like this. And so here's an example of one of the trials. Right? The object is rotating with these fidgets and stuff like that. Carlo went obviously crazy, but he succeeded, I would say. And here's an example of the task. So the real object, okay, we are manipulating stereo and motion and a combination of the two. Oh, this is actually I forgot that we have the video also in the dark. So because obviously they were looking at this thing in the dark, because we wanted to reduce other things, right? But the bottom line is that there was no Q2 flatness because there was no monitor there. And so actually, this is the baseline of it. The baseline is when the stimulus was horizontal, so you didn't have that much information. Already people actually were picking up something. So here's the object depth. We had two depths simulated here, almost 30, almost 40, something like that, right? And this is your perceptual task in manual estimation. You see that you're already with the baseline, what we call residual cues, you add information. When you added stereo, you had more information. When you added motion, you had basically, to this baseline, you had almost the same performance as stereo. And when you both add both, the multiple cue stimuli was even perceived even deeper. Okay, so you go from a certain amount of depth, and the more cues you add in a real-world situation, the deeper the stimulus is, as predicted by the intrinsic constraint model. And the grasp task gave us basically the same results, if not even cleaner, right? So when you grasp, it's not that you're isolating all the cues, you just consider it stereo, you're doing exactly the same game. And it's very difficult to discriminate between these two patterns of results, right? But they are completely different tasks. And so, to conclude, I would say that, the first thing is that empirical evidence indicates that 3D vision is not very difficult, and I'm still looking for be convinced of the opposite. And the conclusion number 2 is that I would say that this model is a decent predictor of the results, in the sense that it predicts things that would be unpredictable by the other models. I'm not saying it's the right model, because there's no such thing in science, but it's something that is promising. And perhaps, and this is what I'm adding today, the visual system has learned this thing by exploring these highly correlated signals that are present in the personal space, the peripersonal space. And the perception, again, is what presents the mapping. So, in a way, vision serves action. This is the real role of vision. But what I'm proposing is that we have to think about it in terms of, do we really need this veridical Euclidean representation to act on the world? And in fact, I think it doesn't. It does not require veridical representation. And what I think of perception is not that it's something else. Perception actually is basically the image, the conscious image of your action space, of your motor planning, and so forth. And perception and motor mapping are always, I think, updated. And this is what we are working on now, the fact that we think that if you change that line, if you change that space, in the peripersonal space, then you can change action and perception at the same time. And, well, obviously, I thank Corrado Kautek of the University of Florence, who gave me the paper, and so, and then, obviously, Jan Koenderink, who wrote it, and Andrea, obviously. Carlo Campagnoli is at Princeton, and, our friend Euclid, who did this part. Thanks.